Okay, so in this problem, we're going to make some assumptions, right? So we've got this tank, and the tank, we'll say it looks like this. They said it's a very wide tank. So what they're getting at is this is a really big tank compared to the hole at the bottom. So we've got this giant tank, and it's 4.7 meters deep from top to bottom. Okay, so in this problem, it'd be easiest to use Bernoulli's equation. So we can analyze the top versus the bottom. So I got this spigot down here and I got some water coming out, and I want to know what the velocity of the water at the bottom is. All right, so we can make the assumption first off, because this is really wide. If you think about the water level in here, all right, so here's the water level. As this thing drains, if I have like a little spigot down here and I'm draining a 4.7 meter tall tank, if you think about when you first open that spigot, the amount of water that comes out, how much this water level is going to drop, it's basically going to be zero, right? So this water level up here is moving at about 0 meters per second. Now, this isn't true, right? But we're making an assumption because it says this is much larger than this. If you let this go for long enough, you could actually measure the speed, right? So we'll say the velocity of the water at the top is about 0 meters per second. And we're given this height over here, right? So that's going to be our delta y to the top. So Bernoulli's equation, right? If you remember this, P, we'll call P top plus rho g delta y at the top plus 1/2 rho v at the top squared equals these same values at the bottom. So the pressure at the bottom plus rho g delta y at the bottom plus 1/2 rho v at the bottom squared. Okay, so now let's look at what we can get rid of because of our assumptions. So because the velocity of the water at the top is 0 meters per second, I can say this part right here is 0 because v at the top equals 0. Okay, and then down here at the spigot, right, it says it's at the bottom of a very wide thing. So down here, delta y is 0. There's no height, right, because it's shooting out basically at ground level. So that means in this term at the bottom, I can get rid of this because the height at the bottom equals 0. So I've simplified this equation up a bit now, right? And then I can also get rid of these pressures, right? Because this tank, both of these are being exposed to atmospheric pressure, right? So this water, as it comes out, is exposed to the atmosphere. It's pushing all over it. And up here at the top of the tank, it's being exposed to atmospheric pressure, right? So that means that both of these are going to go away. So this is simplified a lot, and it's just become a conservation of energy equation. So I have rho g delta y at the top equals 1/2 rho v at the bottom squared. And notice density of water is in both of these, right? So I can cancel it out because it's a constant. So I have g delta y at the top equals 1/2 velocity at the bottom squared. I can solve for b, so that's going to be 2g delta y at the top. Square root of that will give me my velocity at the bottom. And that, when you plug in those numbers, comes out to 9.6 meters per second. So really kind of a simple conservation of energy problem once you use some assumptions to get rid of some things.